In probability theory and statistics, the chi-squared distribution with k degrees of freedom is the distribution of a sum of the squares of k independent standard normal random variables. It is a special case of the gamma distribution and is one of the most widely used probability distributions in inferential statistics, e.g., in hypothesis testing or in construction of confidence intervals, when it is being distinguished from the more general non-central chi-squared distribution. This distribution is sometimes called the central chi-squared distribution. The chi-squared distribution is used in the common chi-squared tests for goodness of fit of an observed distribution to a theoretical one. The independence of two criteria of classification of qualitative data, and in confidence interval estimation for a population standard deviation of a normal distribution from a sample standard deviation. Many other statistical tests also use this distribution, like Friedman's analysis of variance by ranks. Definition: if Z1, Zk are independent, standard normal random variables, then the sum of their squares is distributed according to the chi-squared distribution with k degrees of freedom. This is usually denoted as the chi-squared distribution has one parameter, k, a positive integer that specifies the number of degrees of freedom introduction to the chi-squared distribution. The chi-squared distribution is used primarily in hypothesis testing. Unlike more widely known distributions such as the normal distribution and the exponential distribution, the chi-squared distribution is rarely used to model natural phenomena. It arises in the following hypothesis tests, among others: chi-squared test of independence in contingency tables, chi-squared test of goodness of fit of observed data to hypothetical distributions, likelihood ratio test for nested models, log rank test in survival analysis, Cochrane-Mantel-Henschel test for stratified contingency tables. The primary reason that the chi-squared distribution is used extensively in hypothesis testing is its relationship to the normal distribution. Many hypothesis tests use a test statistic, such as the t-statistic in a t-test. For these hypothesis tests, as the sample size n increases, the sampling distribution of the test statistic approaches the normal distribution. Because the test statistic is asymptotically normally distributed, provided the sample size is sufficiently large, the distribution used for hypothesis testing may be approximated by a normal distribution. Testing hypotheses using a normal distribution is well understood and relatively easy. The simplest chi-squared distribution is the square of a standard normal distribution. So wherever a normal distribution could be used for a hypothesis test, a chi-squared distribution could be used. Specifically, suppose that Z is a standard normal random variable, with mean equals 0 and variance equals 1. Z tilde n. A sample drawn at random from Z is a sample from the distribution shown in the graph of the standard normal distribution. Define a new random variable Q. To generate a random sample from Q, take a sample from Z and square the value. The distribution of the squared values is given by the random variable Q equals Z2. The distribution of the random variable Q is an example of a chi-squared distribution. The subscript 1 indicates that this particular chi-squared distribution is constructed from only one standard normal distribution. A chi-squared distribution constructed by squaring a single standard normal distribution is said to have one degree of freedom. Thus, as the sample size for a hypothesis test increases, the distribution of the test statistic approaches a normal distribution, and the distribution of the square of the test statistic approaches a chi-squared distribution. Just as extreme values of the normal distribution have low probability, extreme values of the chi-squared distribution have low probability. An additional reason that the chi-squared distribution is widely used is that it is a member of the class of likelihood ratio tests. LRTs have several desirable properties. In particular, LRTs commonly provide the highest power to reject the null hypothesis. However, the normal and chi-squared approximations are only valid asymptotically. For this reason, it is preferable to use the t-distribution rather than the normal approximation or the chi-squared approximation for small sample size. Similarly, in analyses of contingency tables, the chi-squared approximation will be poor for small sample size, and it is preferable to use the Fisher exact test. Ramsey and Ramsey show that the exact binomial test is always more powerful than the normal approximation. Where are the squared normal distributions? If the chi-squared distribution is used because it is the sum of squared normal distributions, why are the squared normal distributions in contingency tables analyzed with a chi-square test? The answer can be traced back to the normal approximation to the binomial distribution. Consider an experiment in which 10 fair coins are tossed, and the number of heads is observed. This experiment can be modeled with a binomial distribution, with n equals 10 trials and p equals 0.5 probability of heads on each trial. Suppose that heads is observed 1 times in 10 trials. What is the probability of a result as extreme as 1 heads in 10 trials, if the probability of heads is p equals 0.5? 3 methods to determine the probability are: calculate the probability exactly using the binomial distribution, estimate the probability using normal approximation to the binomial distribution, estimate the probability using a chi-squared test. This result will be the same as the result for the normal approximation. Calculation using the exact binomial and the normal approximation may be performed using http://vasistats.net/binomial.html. Calculation of the chi-square probability may be performed using http://vasistats.net/csfit.html. Using the binomial distribution, the probability of a result as extreme 1 heads in 10 trials is the sum of the probabilities of 0 heads, 1 head, 9 heads, or 10 heads. Notice that this is a two-tailed or two-sided test. This test gives p equals 0.0215. Using the normal approximation to the binomial distribution, the probability of a result as extreme 1 heads in 10 trials is p equals 0.0271. The chi-squared test is performed as follows. The observed number of heads is 1, and the observed number of tails is 9. The expected number of heads equals expected number of tails equals 10 * 0.5 equals 5. The difference between the observed and expected is 1 to 5 equals -4 for heads, and 9 to 5 equals 4 for tails. The chi-squared statistic is for the chi-squared test. The probability of a result as extreme as 1 heads in 10 trials is p equals 0.027, the same as the result using the normal approximation. That is, the probability that the chi-squared statistic with 1 degree of freedom is greater than 4.9 is p equals 0.027. Lancaster shows the connections among the binomial, normal, and chi-squared distributions, as follows. De Moivre and Laplace established that a binomial distribution could be approximated by a normal distribution. Specifically, they showed the asymptotic normality of the random variable where m is the observed number of successes in n trials, where the probability of success is p, and q equals 1 minus p. Squaring both sides of the equation gives using n equals np plus n equals m plus, and q equals 1 minus p. This equation simplifies to the expression on the right is of the form that Pearson would generalize to the form, where equals Pearson's cumulative test statistic, which asymptotically approaches a distribution, equals the number of observations of type I, equals the expected frequency of type I, asserted by the null hypothesis that the fraction of type I in the population is equals the number of cells in the table. In the case of a binomial outcome, the binomial distribution may be approximated by a normal distribution. Because the square of a standard normal distribution is the chi-squared distribution with 1 degree of freedom, the probability of a result such as 1 heads in 10 trials can be approximated either by the normal or the chi-squared distribution. However, many problems involve more than the 2 possible outcomes of a binomial, and instead require 3 or more categories, which leads to the multinomial distribution. Just as de Moivre and Laplace sought for and found the normal approximation to the binomial, Pearson sought for and found a multivariate normal approximation to the multinomial distribution. Pearson showed that the chi-squared distribution, the sum of multiple normal distributions, was such an approximation to the multinomial distribution characteristics. Further properties of the chi-squared distribution can be found in the box at the upper right corner of this article. Probability density function. The probability density function of the chi-squared distribution is where gamma denotes the gamma function, which has closed-form values for integer k. For derivations of the PDF in the cases of 1, 2 and k degrees of freedom, see proofs related to chi-squared distribution. Differential equation. The PDF of the chi-squared distribution is a solution to the following differential equation. Cumulative distribution function. Its cumulative distribution function is where gamma is the lower incomplete gamma function and p is the regularized gamma function. In a special case of k equals 2, this function has a simple form, and the form is not much more complicated for other small even k. Tables of the chi-squared cumulative distribution function are widely available, and the function is included in many spreadsheets and all statistical packages. Letting Cherneff bounds on the lower and upper tails of the CDF may be obtained for the cases when the tail bound for the cases when, similarly, is for another approximation for the CDF modeled after the cube of a Gaussian. See under noncentral chi-squared distribution. Additivity. It follows from the definition of the chi-squared distribution that the sum of independent chi-squared variables is also chi-squared distributed. Specifically, if chi equals 1 n are independent chi-squared variables with chi equals 1 n degrees of freedom, respectively, then y equals x1 plus xn is chi-squared distributed with k1 plus not degrees of freedom. Sample mean. The sample mean of d chi-squared variables of degree is distributed according to a gamma distribution with shape and scale parameters. Asymptotically, given that for a scale parameter going to infinity, a gamma distribution converges towards a normal distribution with expectation and variance, the sample mean converges towards. Note that we would have obtained the same result invoking instead the central limit theorem, noting that for each chi-squared variable of degree the expectation is, and its variance, entropy. The differential entropy is given by where psi is the gamma function. The chi-squared distribution is the maximum entropy probability distribution for a random variate x for which n are fixed. Since the chi-squared is in the family of gamma distributions, this can be derived by substituting appropriate values in the expectation of the log moment of gamma. For derivation from more basic principles, see the derivation in moment generating function of the sufficient statistic. Noncentral moments. The moments about zero of a chi-squared distribution with k degrees of freedom are given by cumulants. The cumulants are readily obtained by a power series expansion of the logarithm of the characteristic function. Asymptotic properties by the central limit theorem. Because the chi-squared distribution is the sum of k independent random variables with finite mean and variance, it converges to a normal distribution for large k. For many practical purposes, for k greater than 50 the distribution is sufficiently close to a normal distribution for the difference to be ignored. Specifically, if x tilde chi-squared, then as k tends to infinity, the distribution of tends to a standard normal distribution. However, convergence is slow as the skewness is and the excess kurtosis is 12k. The sampling distribution of lane converges to normality much faster than the sampling distribution of chi2, as the logarithm removes much of the asymmetry. Other functions of the chi-squared distribution converge more rapidly to a normal distribution. Some examples are, if x tilde chi-squared then is approximately normally distributed with mean and unit variance. If x tilde chi-squared then is approximately normally distributed with mean and variance, this is known as the Wilson-Hilbert transformation. Relation to other distributions. As if then has the chi-squared distribution. As a special case, if then has the chi-squared distribution. If and then. If then is an exponential distribution. If then. The chi-squared distribution is a special case of type 3 Pearson distribution. If and are independent then. If then is a transformation of Laplace distribution. If then. Chi-squared distribution is a transformation of Pareto distribution. Student's t-distribution is a transformation of chi-squared distribution. Student's t-distribution can be obtained from chi-squared distribution and normal distribution. Noncentral beta distribution can be obtained as a transformation of chi-squared distribution and noncentral chi-squared distribution. Noncentral t-distribution can be obtained from normal distribution and chi-squared distribution. A chi-squared variable with k degrees of freedom is defined as the sum of the squares of k independent standard normal random variables. If Y is a k-dimensional Gaussian random vector with mean vector mu and rank k covariance matrix C, then x equals tc-1 is chi-squared distributed with k degrees of freedom. The sum of squares of statistically independent unit variance Gaussian variables which do not have mean zero yields a generalization of the chi-squared distribution called the noncentral chi-squared distribution. If Y is a vector of k(i), standard normal random variables and A is a k times k symmetric, idempotent matrix with rank k-n, then the quadratic form YTAY is chi-squared distributed with k-n degrees of freedom. The chi-squared distribution is also naturally related to other distributions arising from the Gaussian. In particular, Y is F distributed, Y tilde F if where x1 tilde chi-squared and x2 tilde chi-squared is statistically independent. If X is chi-squared distributed, then is chi distributed. If x1 tilde chi2 k1 and x2 tilde chi2 k2 are statistically independent, then x1 plus x2 tilde chi2 k1 plus k2. If x1 and x2 are not independent, then x1 plus x2 is not chi-squared distributed. Generalizations. The chi-squared distribution is obtained as the sum of the squares of k independent, zero mean, unit variance Gaussian random variables. Generalizations of this distribution can be obtained by summing the squares of other types of Gaussian random variables. Several such distributions are described below. Linear combination. If a chi-square random variables and then a closed expression for the distribution of is not known, it may be, however, calculated using the property of characteristic functions of the chi-squared random variable. Chi-squared distributions. Noncentral chi-squared distribution. The noncentral chi-squared distribution is obtained from the sum of the squares of independent Gaussian random variables having unit variance and non-zero means. Generalized chi-squared distribution. The generalized chi-squared distribution is obtained from the quadratic form ZAZ where Z is a zero mean Gaussian vector having an arbitrary covariance matrix, and A is an arbitrary matrix. Gamma, exponential, and related distributions. The chi-squared distribution x tilde chi-squared is a special case of the gamma distribution, in that x tilde gamma using the rate parameterization of the gamma distribution using the scale parameterization of the gamma distribution, where k is an integer. Because the exponential distribution is also a special case of the gamma distribution, we also have that if x tilde chi-squared, then x tilde exp is an exponential distribution. The Erlang distribution is also a special case of the gamma distribution, and thus we also have that if x tilde chi-squared with even k, then x is Erlang distributed with shape parameter k2 and scale parameter 1/2. Applications. The chi-squared distribution has numerous applications in inferential statistics, for instance in chi-squared tests and in estimating variances. It enters the problem of estimating the mean of a normally distributed population and the problem of estimating the slope of a regression line via its role in students' t-distribution. It enters all analysis of variance problems via its role in the f-distribution, which is the distribution of the ratio of two independent chi-squared random variables, each divided by their respective degrees of freedom. Following are some of the most common situations in which the chi-squared distribution arises from a Gaussian distributed sample. If x1, xn are I, d, n random variables, then where the box below shows some statistics based on chi-normal, I equals 1, k, independent random variables that have probability distributions related to the chi-squared distribution. The chi-squared distribution is also often encountered in magnetic resonance imaging. Table of chi2 value versus p-value. The p-value is the probability of observing a test statistic at least as extreme in a chi-squared distribution. Accordingly, since the cumulative distribution function for the appropriate degrees of freedom gives the probability of having obtained a value less extreme than this point, subtracting the CDF value from 1 gives the p-value. The table below gives a number of p-values matching to chi2 for the first 10 degrees of freedom. A low p-value indicates greater statistical significance, i.e., greater confidence that the observed deviation from the null hypothesis is significant. A p-value of 0.05 is often used as a cutoff between significant and not significant results.